is the 2017 AP Calculus BC free response question on the calculator section, and this is question number 1. Question number 1 states a tank has a height of 10 feet. The area of the horizontal section of the tank at height h feet is given by the function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values for h of h are given in the table above. Question A says use a left Riemann sum with 3 subintervals indicated by the data in the table to approximate the volume of a tank. So what we're going to do here is we're going to take these differences, 2, 3, and 5, and multiply it by the left hand. So we're taking these values right here. And so this corresponds to sort of a triangle that is going on between each value right here. And then this will give us an estimate of the volume. So we're going to say 2 times 50.3 plus 3 times 14.4 plus 5 times 6.5, which gives us 176.3, and we can't forget the unit, which is given in cubic feet, so feet cubed. And that is your answer for the question number 1. B asks, does the approximation in part A overestimate or underestimate the volume of the tanks? Explain your reasoning. So first of all, we're going to go back to the chart and see whether it's an overestimate or an underestimate. And when we do this, we got to read the question again carefully, and I'm going to highlight this section right here. In particular, I want to focus on this section. So when a function is decreasing and we're taking the left-hand Riemann sum, I'm going to try to demonstrate this in pictures so that it's easier to see. What I've done here is drawn a simple sketch of the graph that estimates the values given in this chart. And these values are no by any means estimates, so we can actually plot these points and get an idea of what the graph is going to look like. And this is sort of going to help us realize what the left Riemann sum is going to give us in terms of an overestimate or an underestimate. So if we just color in this area right here, the blue line is sort of the estimate of the actual equation that A of h models. But we can see that by taking the left-hand Riemann sum, the entire blue area that is covered here is basically the area, except excluding this part, because that would be included in the right Riemann sum, which includes this value. But all we've taken is these L-shaped sums right here, and may be confusing because they're overlapping, but we taken the difference of 2 and multiplied it by what is right here, 15.3, and as you can see, the area is way over the estimate of the actual curve. So we can clearly say now that it's an overestimate. The other component to this question is give your reasoning, and that's when I'm going to come back to the question itself and the explanation of the question, and I've highlighted here that says decreases. So this is an overestimate because A of h is decreasing, and therefore that means that, and we're taking the left-hand Riemann sum. So this is sort of the entire explanation of how you come up with what is an overestimate or an underestimate. And this graph wouldn't count as an explanation, but gets you the idea of why it is. Question C asks, the area in square feet of the horizontal cross-section at height h feet is modeled by the function f given by f of h equals 50.3 over e to the 0.2 h plus h. Based on this model, find the volume of the tank, indicate units of measure. Now, in order to do this question, which is quite simple, if you get the concept of what is being asked here. So f of h gives some sort of cross-sectional area of this weird tank that may have some sort of shape. And each cross-section, no matter what shape, is given by f of h. Now, in order to find the volume, we're going to have to multiply it by the height, h. And h is from 0 to 10, and it's constant. It's a constant change. So there's really no unexpected values in between. But the cross-sectional area, on the other hand, this area is modeled by f of h, which is not constant, as you can see. It's some sort of equation. So we can't just multiply one cross-sectional area and multiply it by the height to get the volume. So what we're going to do is take the integral from 0 to 10 of f of h dh, and that's going to give us the answer because we're taking little tiny slivers of the surface area and we're multiplying it throughout the height from 0 to 10, which is h. So now we can use our calculator, so we're going to plug that value back in here and we get an answer approximation of about 101.325, and let's never forget the units, which is given by cubic feet. Finally, D says water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26 foot per minute. Using the model from part C, find the area at which the volume of water is changing with respect to time when the height of the water is 5 feet. Indicate units of measure. Let's start by analyzing what this question is really asking for. And we find that it's actually just asking for the rate at which the volume of water is changing with respect to time. So that's easy enough. That is just dv dt. And we're going to evaluate that at h equals 5 because it says when the height of the water is at 5 feet. But these units don't match up because one is volume with respect to time, and we're finding the answer in terms and with respect to height. So what do we do then? Well, we know that it gives us a few key information that is going to help us find the answer. When the height of the water is at 5 feet, the height is increasing at a rate of 0.26 foot per minute. So let's write that down. We can say that dh dt equals 0.26. And in order to get dv dt, we really want to find something to multiply this by that'll give us this in terms of volume. So we can start by using this equation, dh dt, and saying what can we multiply it by that gives us dv dt. So obviously we would need some sort of dv in there. And then we realize that we're actually not going to need dh, so we can cancel that. So if we multiply these two together, we can cross these out and we're going to get dv dt. And then we can plug in h equals 5 into both of these equations. But before we get ahead of ourselves, we can first say that now that we know that we have to multiply by dv dh, we got to check if we actually know what dVdh is. So, well, this can be rewritten as ddh of the volume. So the derivative, the height derivative of the volume. And if you scroll up and look ahead, using the model from part C, this is a key information too. So we're going to scroll up ahead and realize that the volume is just this equation right here, except we don't really have limits of integration now that we're dealing with related rates. So we're going to say this is ddh of the integral of f of h dh. But there's something quite interesting about this. If you recall the fundamental theorem of calculus, we can say that the derivative of an integral that has the same values of, well, let's call these values, I guess. Then you can say that this is just equal to f of h. So now we found that dv dh is just, in fact, f of h. So now all we have to do is multiply dh dt at h equals 5 by dv dh at h equals 5. So then we already know this one. This one just simply becomes 0.26. And then in order to find dv dh at h equals 5, we just find f of h, which is given up here. We're just going to bring that all the way down here and say 50.3 all over e to the 0.02 h plus h. And we're going to evaluate this at h equals 5. Finally, all we're doing here is plugging these into the calculator. Actually, I made an error here. This is supposed to be 0.2 h. And we're going to plug in h equals 5 into these values. And our final answer should come out to about 1.694. And volume with respect to time. So the units of measurement are going to be feet cubed per minute.